All right, welcome back. We're now in topic 12, which is, by the way, the last topic that's in Chem 151. And topic 12 covers the energy changes in chemical reactions. This topic is important because a lot of times in the world, we're not so concerned with what's produced in a chemical reaction, but rather we're trying to harness the energy that's behind the chemical reaction. For example, most automobiles still run on gasoline. And gasoline is a carbon-based compound. It's an organic compound that gets combusted. That's why we call it a combustion engine. Well, what happens is in the combustion reaction, as you are aware from topic 9, is that carbon dioxide and water are produced. But we don't actually care about carbon dioxide or water in the fact of trying to drive the car. We only care about the energy output that is produced from a combustion reaction. And it's the energy output that is what drives the car. And so in this topic, we're going to be analyzing the energy output or input of chemical reactions. We're going to be more focused on the energy. And so in this first section, we're going to need to take a look at energy a little bit more closely. And we're going to need to make sure we're familiar with some terms before we start to get into the nitty-gritty of those energy changes. And so we're going to do a little bit of introduction. This is the introduction to thermochemistry terms and concepts. All right, so we've talked about energy before. You've seen energy before. We just didn't really get into it too much. And so we're going to dive into it a little bit more now. And so to remind you, what is the definition of energy? It's the ability to do work or transfer heat. Now, work and heat are actual physical terms. We'll talk about that in a little bit. But essentially, energy just makes things happen. We talked about in previous topics that energy could be divided into two main categories, and that's potential energy and that's kinetic energy. So potential energy and kinetic energy, you can think of these two big umbrellas that all these other different types of energies fall under. Reminder that potential energy is energy that is stored due to either position or the chemical arrangement of the atoms. And then kinetic energy, that kinetic word, is any energy due to motion. Well, one of the energy types that we're going to be working with in this unit is called thermal energy. And thermal energy, as you may have guessed, has to deal with heat. So thermal energy actually falls under the kinetic energy umbrella because, when things are moving quickly, that's when we feel that things are getting hotter. And so thermal energy tends to fall under that umbrella. So we need to now get into this word heat, okay? And oftentimes we use heat and thermal energy interchangeably, but they're actually two different things. Thermal energy is the actual essence. It's the actual object. You can think of that as the noun, if you will, to bring a little English into this. Whereas heat is a process. Heat is a verb. Heat is the transfer of the thermal energy. And thermal energy will always go from the hot object to the cold object. Remember that because that'll come into play later. And so it'll always go from the hot object to the cold object. There's no such thing as cold energy. It's just, if you feel cold, it's the absence of thermal energy. It's the absence of heat. And so the heat always goes from hot to cold until it reaches thermal equilibrium, and that's when both objects are the same temperature. So you may have realized this or experienced this in real life. Sometimes you get into a pool and it feels really cold until your body adjusts, until that thermal equilibrium is reached, and then after a while you're like, oh, it's not so bad in here. Well, that's because your body has reached thermal equilibrium. Now, whether or not you can handle thermal equilibrium is another thing. But that's why, if you stay in a pool for long enough or a hot tub or anything, it takes your body a little bit of time to adjust, but eventually it will if you can handle it. And so that's what thermal equilibrium is. Now, to talk about the unit of energy that we're going to be looking at, there's actually two units of energy. The one that you're most familiar with from previous units or topics is the joule, which is a capital J, but equally used is the calorie, C-A-L. Notice that's a lowercase calorie, lowercase C-A-L. And so 1 calorie is exactly equal to 4.184 joules. This is an exact measurement, so if you use this to calculate anything, significant figures will not play a factor. Another thing to notice, and I'll try to remind you of this later on, is this unit of the calorie is actually based off of liquid water. And we'll get to that later. So 1 calorie, that unit of 1 calorie, what did they base that off of? They based it off of water. And I'll talk about that later when we talk about specific heat. Now, when you hear calories, you probably think of calories on the back of your food labels, like your nutrition facts, right? Well, if you were to look at the back of your, food and it said 100 calories, you would actually notice the calorie is a big C calorie. And 1 big C calorie is actually the same as 1 kilocalorie, which we know is 1,000 little C calories, right? So if you eat 100 calories, what you're really consuming is you're consuming 100,000 little C calories. Now, before you freak out and think you're overeating, don't worry. When they say like the average diet is 2,000 calories a day, they're basing it off of the big C calorie, right? So we should be consuming quite a bit of little C calories. But just that's something to point out and just something to notice. Okay, we need to be familiar with these two terms, system and surroundings. You may have heard this before in another science class. We haven't really talked about it much up until this point, so this is a good opportunity to at least teach it or revisit it if you've heard of it before. The system is very important. When you're talking about processes where something's coming and going, like energy, you need to make sure you define what the system is, okay? Because we have to be able to define the direction of heat flow. And so the system in chemistry is the part we care about, and that's usually the reactants and the products. It's where the chemical reaction is taking place. So a lot of times this is the beaker, the test tube, whatever, wherever the reaction in question is happening. And then what we do is we analyze, is energy leaving the system or is it going into the system? And so the system is what we care about, and the surroundings is basically everything else. The surroundings is the room, and the surroundings is, everything beyond the room. So we analyze what's happening between the system and the surroundings. So before you can do that, you need to identify what the system is. There are 3 types of systems. The one that we'll be focusing on in this unit is system C, but I'm going to cover all 3. So the first system is an open system, and that's where mass and heat can transfer, it can pass through easily. So example down here, letter A, this is a round bottom flask. You notice that, it's glass. Glass is not a good insulator of heat. If you've ever touched hot glass, you'll know that. It'll transfer energy real easily. So it's going to let heat go back and forth, but also notice it's not capped. So mass can go back and forth, like water vapor could leave. The next type of system is a closed system. So that would be like letter B. Notice that it's capped now. So now mass can't leave, but heat still can. Heat's allowed to go back and forth. Well, when you're analyzing heat transfer specifically, if you're analyzing a reaction where the heat is the primary focus, you don't want to use systems A or B. You want to use system C, which is an isolated system, which means not only is it capped, but it's also insulated. So all the heat transfer that's happening is happening inside here. We don't have to worry about heat leaving or heat going in to mess up our results. Everything's contained within the container, right? So the isolated system is the one that's important. All right. Continuing on with some vocabulary. I know this is a lot of vocab, so this is just some things that we need to be aware of. You're going to hear about this word spontaneous, and you'll actually look at spontaneous a little bit more in Chem 152, but I want to at least introduce it to you now. So when we're talking about chemical reactions and we're talking about energy involved in chemical reactions, we can say a chemical reaction is either spontaneous or non-spontaneous. Now, a lot of times when students hear spontaneous, they think fast, right? They think, oh, if something happens spontaneously, it happens fast. That's not true. A lot of reactions happen spontaneously, but they happen very slow. So what does spontaneous mean then? Essentially what it means is it happens on its own, right? The reaction does not need a scientist to do anything to interject. It's a reaction that's going to happen naturally, if you will. So a great image to illustrate this is consider this ramp, okay? And consider you have a ball, right? You have a ball on the top of the ramp, ball on the bottom of the ramp, or same ball, doesn't really matter. Okay, so if I place the ball at the top of this ramp and then just let go, naturally that ball is going to go down the hill. Okay, it's going to go down the ramp. That's spontaneous, right? That doesn't need any intervention from me. But if I wanted to push this ball up the ramp, that's going to take some outside intervention. That's not going to happen naturally. Something needs to intervene to make that happen. That's really as in-depth as we're going to go with spontaneous. I just want you to be familiar with that term, okay? So spontaneous means it happens on its own. All right, a few more things to be aware of, and then we're done with section 1. We've talked about the terms exothermic and endothermic, but I want to revisit those. So we're talking about thermal energy going from warmer objects to cooler objects. And then we also talked about, identify the system. If energy leaves the system, that's going to be known as an exothermic reaction. When energy leaves the system in question, that's known as an exothermic reaction or exothermic process. You can think of heat is exiting, right? But if heat goes into the system, if heat enters, if you will, okay, think of the word enter, if heat enters the system, that's an endothermic process. Now we can graph these, and I want to just briefly show the graph. I know the print's kind of small, but here on the y-axis we have energy, and then on the x-axis we have time. And notice for a chemical reaction, okay, this would be your reactants, and then this would be your products. Notice that the reactants is higher in energy than the products, right? Why would that be? Why would the reactants be higher in energy than the products? Because as a result of the chemical reaction, which by the way is shown with this kind of hill thing, as a result of that chemical reaction, the products is lower in energy because energy was released as a result of that reaction. And remember, when energy is released, your ending products must be lower in energy because that reaction got rid of energy. That's an exothermic reaction. But if you have your reactants here and then your final products are higher in energy, why would your final products be higher in energy than your reactants? Well, energy must have been absorbed or entered in that process. And so that would be an endothermic reaction. Now, real quickly, why in both of these, why does energy go up and then eventually, drop to what it needs to be? Well, we're not going to get into this right now, but you may have heard this from like a biology class. This is known as activation energy. Every reaction needs a little bit of activation energy to get it going, right? So that activation energy is what's defined as, the peak of that. But then once it reaches the activation energy and the energy just kind of goes, then, you just basically look, is the reactants higher than the products or is the reactants lower than the products? And that's going to give away what kind of reaction this is taking place. Now, we want to make sure we understand in a physical sense, when you're in the lab, what does exothermic and endothermic look like? Think about if you were holding an Erlenmeyer flask. Let's say you were holding this flask right here, and an exothermic reaction was taking place in that flask. So as a result of this reaction, what's going on inside, it's an exothermic reaction. Energy is leaving. Well, where does that energy go when it leaves the flask? Well, it goes into your hands because you're holding the flask. What are you going to feel if energy is going into your hands? It's going to feel hot, right? So if I'm holding a flask that there's an exothermic reaction taking place, it's going to feel hot. On the other hand, if I'm holding a flask that's endothermic, okay, remember endothermic heat is entering, well, where is the heat coming from that's entering this flask? If I'm holding the flask, it's actually coming from my hand, which is kind of weird to think about, right? Thermal energy is leaving my hand and going into the flask, right? It's drawing energy from the surroundings. And so if I hold a flask that is containing an endothermic reaction, it's going to feel cold because thermal energy leaving my hand makes me feel cold. So in the last minute and a half of this video, we're going to do an example where I have 4 processes below, and I've identified the system for you. I have to do that, otherwise you can't answer this question. And so in the processes below, I want you to indicate whether the process is exothermic or endothermic. Let's do the first one as an example. Okay, getting into a hot tub, you are the system. So think about this, okay? This is the hot tub, okay? You get in here. All right. First thing I do is I say, okay, map where the energy is going. Remember, thermal energy always flows from a hot object to a cold object. If you're getting into a hot tub, I'd imagine the water in the hot tub is hotter than you. So energy, okay, in the water is going to go into you, right? And so now you have to think, okay, what was the system? We said the system was you. And so if you are the system and energy is going into you, what kind of process is that? Well, if heat is entering the system, that's endothermic, right? Go ahead and try the other 3. Pause the video, try the other 3, and then just hit play and resume to get the answers. All right, so what I've got in these last few seconds is I just got the drawings. We're going to try to quickly go through these. So in the walk-in freezer, okay, you are warmer than the freezer, so energy is leaving you and going into the freezer. Well, the system is the freezer, so the freezer is absorbing the energy coming from your body. So that also is going to be endothermic. For the ice cream sitting out on the counter, the room energy is going to go into the ice cream because the ice cream is colder. The room is the system, and so since the energy is leaving the system, it's going to be exo. And in the last one, it's exo because heat's leaving.